In the previous lecture, we talked about backstepping method to construct a feedback law to stabilize the origin of a system that's in strict feedback form. Okay, we talked about it in general terms, and in this lecture we will apply that method to some simple examples so that we become more familiar with the method. Okay, so this is our first example from the text. Okay, it's 14. Stabilize the origin of the following second order control system. x1 dot equals x1 squared minus x1 cubed plus x2, and x2 dot equals u. Okay. Now this system is in strict feedback form. Remember the notation that we introduced in the previous lecture. We had eta dot equals f eta plus g eta times xi and xi dot equal u. Now in this case, note that eta is x1, can be taken to be x1, and xi is x2. F of eta is then this term here, x1 squared minus x1 cubed. G of eta is, well, this x1 we can write as 1 times x1, x2, and x2. Then g of eta is constant, 1. And yes, that's it. So that's how the terms match if you think in terms of the general notation that we introduced in the previous lecture. Okay, so what we're going to do now is we'll try to stabilize the origin of the system x1, x2 by choosing a proper feedback law u. Okay, it will be a function of x1 and x2, and we're going to figure out how to choose or design that feedback law by using backstepping. Okay, so in order for us to be able to apply backstepping, first we need the feedback law in terms of eta, phi of eta, so that this subsystem, the origin of that subsystem, is asymptotically stable. And also we require a Lyapunov function through which that asymptotic stability can be established. So hence, since we're not given that particular feedback law, let's try to come up with one. Okay, phi of eta, it will be phi of x1, and also a proper Lyapunov function, so that we see through it the asymptotic stability of this subsystem. Okay, and then once we have that phi and the Lyapunov function, we can move forward to design our final feedback law using backstepping. Okay. So the very first step, step 1, or even step 0, is find a feedback law. Okay, phi from Rn to R. N was the dimension of, or the size of the vector eta. Eta is in our case x1, and x1 is a scalar. Therefore we're talking about feedback law from the real line to real line, such that the origin of the scalar system, the origin of the system x1 dot equals x1 squared minus x1 cubed plus x2 if we replace x2 with that particle feedback law, x2 equals phi of x1. Let's call this closed-loop system 1 is asymptotically stable. Okay, so in general it's not easy to come up with feedback laws to stabilize the origin. That's why we're developing techniques like backstepping. Okay, but if the system is just first order, then most of the time it's quite straightforward. And in this case, our goal is consider x2 as if it's our control input, and we want to figure out a feedback law, okay, phi of x1, such that when x2 is replaced by that, the closed-loop system, this first order system, has a asymptotically stable origin. Okay. Now let's look at the terms. One way would be just remove everything. Okay. So that x2 is minus x1 squared plus x1 cubed, and then plug in a term that makes the system linear, and then you can check the eigenvalues. Okay. That's one way, but it's not usually necessary, okay, and it's not even from the practical point of view, it's not also economical sometimes to remove all the nonlinear terms, because some of the nonlinear terms may be useful. For instance, this term here, minus x1 cubed, seems to be a useful term because it's always pointing in the right direction. Okay, this is the origin of our first one-dimensional system. x1 cubed, if x1 is here, positive, okay, x1 cubed points to the left. If x1 is here, then minus x1 cubed is positive, it points to the right. Therefore, it's always pointing to the origin, and that's where we want to go. Therefore, this term is useful. Okay. So this is a useful term. Whereas x1 squared is always positive, therefore, it's always pointing to the right, and which means it's not doing us good if we're on the positive half line. Okay, therefore this is potentially a harmful term, and we may want to remove it. Potentially harmful term. Okay, so let phi x1, therefore, no, that is a design problem. There are many answers. This is not an answer. This is not the answer. This is just one answer that will do the job. Okay, so here we have x1 squared, so that we remove this potentially harmful term, and let's also add a linear term minus x1, so that we can perhaps obtain not only asymptotic but exponential stability of the origin. But that's not really important. Then the closed system 1 becomes, under that choice, phi of x1. x1 dot equals minus x1 cubed. Let's call this 2, subsystem 2. For the Lyapunov function, v of x1, 1/2 x1 squared. Okay, so that's the simplest Lyapunov function. Subsystem 2 satisfies Now we have picked a feedback law, okay, for the subsystem, and we picked it as minus x1 squared minus x1. Under that feedback law, the system becomes, the closed loop system becomes that. Closed loop subsystem becomes this. And now we want to establish the asymptotic stability of the origin through a Lyapunov function. We choose a very simple candidate, 1/2 x1 squared, and we're going to now look at its time derivative along the solutions of the system. And if we have a negative definite vita, then we have all that we need to start our backstepping procedure. So what's vita? Vita is x1 times x1 dot. Okay, and that's x1 times this thing, which yields minus x1 squared minus x1 to the 4. Let's call it minus wx1. So clearly w of x1 is positive definite, therefore minus w of x1 is negative definite. Okay. B dot is negative definite, therefore x1 equals 0 is asymptotically stable for the subsystem 2. Okay, now we can start our backstepping procedure. Because we have a working feedback law, okay, for the upper half subsystem, and we have established asymptotic stability through this Liouville function candidate. Step 2. Apply backstepping. Okay, now we can move from this one-dimensional subsystem to the original second-order system. Consider the original right-hand side. And let us introduce, as we did in the previous lecture, the new coordinate, new state variable z, which is difference between x2 and phi of x1. So what we want is, we want this z to go to 0, so that means x2 becomes phi of x1, and when x2 becomes phi of x1, or almost phi of x1, the upper half system becomes this, more or less, x1 that equals minus x1 cube, and we know that that means x1 is converging to 0. If z is converging to 0, x1 is converging to 0, it means phi is converging to 0, and automatically x2 must also converge to 0. Hence x1 and x2 both converge to 0, and we have the asymptotic stability of the origin of the original system. Okay. So what's z in terms of x1 and x2? It's x2 and phi is here, okay, plus x1 plus x2, x1 squared. Okay, so that's our new coordinate. Let's write the system in terms of new set of coordinates. It is x1. Let's write it in terms of x1 and z. Okay, so let's figure out the dynamics of the x1 z system. Okay. So x1 dot is x1 squared minus x1 cube plus x2. So this is the original right hand side for x1 dot. So let's write it. Let's add and subtract this term. Okay. This is clearly 0, and we have the original subsystem. But adding and subtracting has the advantage that this we can write as x1 squared minus x1 cube plus phi x1, and this becomes the desired right hand side for the upper half subsystem, and plus we have x2 minus phi of x1. Okay, what we did, we just reorganize the terms. Now this is, as we said, minus x1 cube. This is the desired right hand side, and this difference we're giving it the name, the new state variable z. Okay. And how about the dynamics for z? What's z dot? Z is here, so z dot is x2 dot minus phi dot. Okay. x2 dot minus phi dot, or x2 dot and plus the dot of this term. What's this dot? It's x1 dot plus 2x1 x1 dot. So it's 1 plus 2x. 1 times x1 dot. Okay. 1 plus 2x1 times x1 dot. And what's x1 dot? x1 dot is here. Okay. That equals. First of all, x2 dot was u, the control input in the original system, and here we have x1 dot in the upper line. So we can write plus 1 plus 2x1 times this term here, minus x1 cube plus z. Okay. Hence, the dynamics of the system in terms of the new coordinates are x1 dot equals minus x1 cube minus x plus z, and then z dot equals u plus 1 plus 2x1 times minus x1 cube plus c. Okay, now the goal is choosing u so that x1z system, the origin of x1z system is asymptotically stable. And how are we going to choose u? Okay, we will be advised by the Lyapunov function, or more correctly, the composite Lyapunov function, which is the original Lyapunov function augmented by a positive definite term relating corresponding to the new state variables. Okay, take the composite Lyapunov function Vc for this system, x1z system, x1 comma z, as the original Lyapunov function for this subsystem, which was 1/2 x1 squared. We know that it works. Plus, we augment it with a positive definite term corresponding to z only, and that would be simply 1/2 z squared. Okay, that is, in terms of the original coordinates x1 and x2, we're talking about the following Lyapunov function: 1/2 x1 squared plus 1/2 z squared. What's z? Z is this. Okay, x2 plus x1 squared. x2 plus x1 squared. So this, therefore, is the new Lyapunov function for the x1, x2 system. Now, how about Vc dot? Now, Vc dot, the question is Vc dot positive definite, or is Vc dot negative definite? Excuse me. Well, Vc dot depends on u, and u is our design variable, our control variable, so we can choose u whatever we like. And what we want is, we want to choose such a u that renders Vc dot negative definite. And to see how to pick that proper u, we have to write Vc dot in its open form. So Vc dot equals, so this is Vc, x1 dot plus z dot. And we have everything we need. This is x1 dot and this is z dot, so let's write them down. So that equals minus x1 squared minus x1 to the 4 plus x1 z. Okay, so that's x1 times x1 dot, or x1 times this term. Okay, it gives us minus x1 squared minus x1 to the 4 plus x1 z. And then we have plus z times z dot. Z dot is here. So we have ZU plus Z times 1 plus 2x1, then minus x1 cube plus Z. Then that equals minus x1 squared minus x1 to the 4. And we can write the remaining terms as Z times something. Z times U plus x1 plus 1 plus 2x1 minus x1 cube plus Z. Okay, and now the question is how to choose U so that we see that is negative definite with respect to x1 and Z. It's clear that what you can do is you can choose U such that it removes all this and replace it with minus Z, for instance, or minus Z cubed. And then the overall thing will be minus x1 squared minus x1 to the 4, and then minus Z to the 2 or Z to the 4 and so on. So choose proper control input to make this term negative so that the overall we see that is negative definite. Okay. Let therefore U equals minus x1. Once again, this is not the only answer, this is just an answer because we're dealing with a design problem. Let U equals minus x1 minus 1 plus 2x1 minus x1 cube plus Z, then add a minus Z. Okay. That is, in terms of the original coordinates x1 and x2, we're talking about U equals minus x1 minus 1 plus 2x1 x1 squared minus x1 cube plus x2. We replace Z with x2 plus x1 squared minus Z, which is x2 plus x1 squared. Okay. So this thing is our feedback law in terms of the original coordinates x1 and x2. Then we see that it comes, okay, this term will cancel this term here, this term will cancel this term here, and finally this minus Z will be left on its own. And that minus Z will multiply that Z, and what we have is minus x1 squared minus x1 to the 4 and minus Z squared. Clearly a negative definite expression. That is, we see that equals minus x1 squared minus x1 to the 4. Let's write we see that in terms of the original coordinates minus Z squared, and Z is here. x2 plus x1 plus x1 squared. Okay. And now we can forget about Z because we have expressed everything in terms of the original coordinates x1 and x2. And what we obtained is the following. For the given original system, okay, x1 that equals something, x2 that equals something, well, x2 that equals U. If you choose U, this expression, then the origin of the closed loop system, okay, so this is our feedback law, is asymptotically stable. How can we establish that? We can establish that using this Lyapunov function, which is positive definite, and if you compute its time derivative along the solutions of the closed loop system, this is what we obtain for VC dot, which is negative definite. Therefore, by Lyapunov's theorem, the origin of the closed loop system is asymptotically stable. Moreover, this can be shown to be, well, it's apparent that it's radially unbounded, okay, with respect to x1 and x2. Therefore, asymptotic stability of the origin is global. So finally, we see positive and radially unbounded, and we see that is negative definite. Okay, therefore the origin x1, x2 equals 0 is globally asymptotically stable. Okay. Now, even though the terms get quite big and ugly quite rapidly in this method, backstepping, the idea is very simple. Okay. All you need is a Lyapunov function and then a feedback law that works for the upper half subsystem to begin with, and then everything is automatic. Now let's put one more brick onto this example and increase the order of the system. And using the results of our previous design, we can now construct a feedback law for a more or higher order system, provided that the second order system appears as a subsystem for that higher order system, which is in strict feedback form. Okay, in other words, consider part B in a sense. Okay, example 14.9. We have now the following system: x1 dot equals x1 squared minus x1 cubed plus x2. The same expression as in the previous example. Now, x2 dot in the previous example was u. Now it's not u, but it equals another state variable, x3, and then x3 dot is the control unit. Okay, now we're talking about the third order system, and using our previous design, we will now try to construct a feedback law in terms of x1, x2, and x3. Okay, that will stabilize the origin of the third order system. Stabilize the origin. Okay, and this is called recursive design. You do the design for second order system, and then you move on to third order system, then you move on to fourth order system, and so on, provided that the structure is in strict feedback form. Okay, recursive design. Okay. Now, we can apply backstepping because the thing is in backstepping form, and we have from the previous example necessary objects. We have feedback law phi, okay, and we have the Lyapunov function v. So from the previous example, we know that the subsystem x1 dot equals x1 minus x1 cube plus x2, x2 dot equals x3. If x3 were to be replaced by the feedback law in terms of x1 and x2, and this feedback law is what we constructed in the previous example, in the previous step, for phi x1 x2 equals minus x1 minus 1 plus 2x1 times x1 squared minus x1 cubed plus x2 minus x2 plus x1 plus x1 squared. Okay, well, I just rewrote what's written here. That's the feedback law, which is known to work as an asymptotically stable, in fact, globally asymptotically stable origin. Where that asymptotic stability can be established by the Lyapunov function 1/2 x1 squared plus 1/2 z squared, z from the previous example, and in x1, in terms of x1 and x2, we see is given here 1/2 x2 plus x1 plus x1 squared. Okay, so we have again everything we need to apply backstabbing. We have a working feedback law, and we have the Lyapunov function through which asymptotic stability of the origin of the subsystem can be established. Now what we're going to do is we want to go one step further and figure out the feedback law that stabilizes the third order system. Okay, again, we write the x1, x2, x3 system in terms of x1, x2, and z as a z system. So this x1 and x2 is eta in our original notation, and this guy, the third guy, is xi. Okay, and z was the difference between xi and the feedback law, which is known to work. So this time, therefore, we let z as the difference between xi, which is x3, and phi, feedback law, x1, x2. Okay. And then we can rewrite the dynamics as x1 dot equals x1 cubed plus x2 dot equals x3. And now we're writing everything in terms of x1, x2, and z, and x3 is z plus phi. Okay, so we have phi of x1, x2 plus z for x3, and finally for z dot we have x3 dot, which is u minus phi dot. Okay, u minus phi dot. And what's phi dot? It's a function of x1 and x2. Therefore, phi dot is partial phi with respect to x1 times x1 dot plus partial phi with respect to x2 times x2 dot. So we can write that as partial phi with respect to x1 times x1 dot, and x1 dot is here x1 squared minus x1 cubed plus x2 plus partial phi with respect to x2 times x2 dot, which is here. Right. Times phi x1 x2 plus c. Okay. And that's it. That's our that's the system in terms of new coordinates. Okay. Now let's call this whole thing as u minus this chunk. U minus the chunk, and the chunk we're describing by this square. Okay. So we're call this thing as square. If you don't like it, you can give it some other name, A, B, C, omega. Okay, now we will try to figure out u so that the origin of x1, x2, z system is asymptotic stable, and we're going to establish the asymptotic stability, and through which we will choose u through the composite Lyapunov function. And that composite Lyapunov function is the previous Lyapunov function augmented by 1/2 z squared term. Z is our new variable. Letting Vc x1, x2, z as the previous Lyapunov function augmented by 1/2 z squared. Right? Vc dot equals, okay, the gradient of v, and then you take the inner product of that gradient with this vector here, okay, and that we can write as partial v with respect to x1 times x1 dot x1 squared minus x1 cubed plus x2 plus partial v partial x2 times x2 dot, which is 5 x1 x2 plus z. Okay, but let's write that term as two separate terms as 5 x1 x2 plus partial v with respect to x2 times z. Okay. And finally we have z times z dot term plus z times z dot. Z dot is u minus square, so that makes gu minus z empty square. Okay. Now, this term appeared also in the previous example. Okay. And we have Vc dot. That's the Vc dot of the previous example, and which we know that it's negative definite. Okay. So negative definite with respect to the pair x1, x2 from the previous example. And then what we require therefore is choose an input u such that this term that remains is also negative with respect to at least z. Okay, so the whole thing is negative definite with respect to x1, x2, and z, our new state variables. And that's easy, choosing u equals this square, okay, and big and ugly term, minus partial v with respect to x2, and then add the final minus z, so that in the end we are left with minus z squared. We obtain Vc dot equals minus x1 square minus x1 to the 4 minus x2 plus x1 plus x1 squared. This was the z of the previous example, and now we have the z of the current example minus z squared. And this whole thing is negative definite with respect to x1, x2, and z, that means it's also negative definite with respect to x1, x2, and x3. So what we have is VC positive definite and radially unbounded. VC dot negative definite, therefore the origin x1, x2, x3 equals 0 is globally asymptotically stable by the Leclerc's theorem. Okay. And this is the feedback law that we established at asymptotic stability with. Okay. Now, these two examples make it more or less obvious that provided that we have a system in strict feedback form and the feedback law and Leclerc function that works for the upper subsystem to begin with, we can just go one step after step and construct a feedback law that would stabilize the origin of the origin system in asymptotic fashion. Okay. So more formally, recursive backstepping can be adapted to the systems that have a special structure, and such systems are called systems in strict feedback form. Okay. So we have the eta as the very first set of states. Eta dot equals f eta plus g eta, and eta is a vector in Rn, times psi. Now let's call it psi1, because we're going to go step after step by psi1, psi2, psi3, and so on. And then psi1 dot. Okay. In the very first general case we considered, this was u, but this doesn't have to be the input directly. Input may appear somewhere downstairs. So let's write it as eta psi1 plus L1 eta psi1, and then that's multiplied by psi2. Then psi2 dot equals H2 eta psi1 psi2 plus L2 eta psi1 psi2 times psi3, and so on. Here, even though eta is a vector in Rn, in general, all the psi's are scalar now. Okay. And you go up to, let's say, k minus 1, h k minus 1, eta psi1 minus 1 plus L k minus 1 eta psi1 k minus 1 psi k, and finally psi k dot is where the input, the control input appears. H k plus Lk times u. Okay. And then how you construct u is, you consider first this guy, and then Xi is sort of your U, and from that you obtain the feedback, well, phi, or you can call it phi1. And then you move on to next, you move on to consider the next line, and then with the feedback law you constructed in the previous step, you now construct Xi3 as if it's your input, and construct a new, larger feedback law, then go one step further, on and on and on, and in the end, you figure out the feedback law that you're looking for. Okay? The conditions that we require to be able to do that, let's list them also. Conditions are eta is in Rn, Xi I are all scalars, I equals 1, 2, k. L, I, those functions are always different than 0, regardless of their arguments, because eventually we may need to divide things by that. Okay. In our examples, in the examples that we considered, the h's were 0 and l's were constant, they were 1. But such examples can be generalized neatly to this extended structure. I equals 1, 2, k, and there exists an initial feedback law phi Rn to R, which is 0 at 0, and the Lyapunov function, and another positive function of was definite and differentiable enough many times, such that eta is negative definite when the first subsystem is considered. Eta And if these conditions are satisfied, the crucial one is that there is a feedback law and a Lyapunov function associated with that feedback law. And if the system has this form, then it's easy to see that the examples that we consider can be, without effort, we generalize to a method where we construct a feedback law to stabilize asymptotically the origin of the original control system.